Thank you very much, Michael, for this very kind introduction. Thank you very much to the organizers for inviting me to give this keynote. I feel honored. The topic today is decoupling, and the couple I'm considering is greenhouse gas emissions and GDP, or income, lifestyle, or happiness, if you wish. I'd like to take stock. I like to show recent work and make suggestions for future research. Actually, it turns out that many of my conclusions relate closely to recent studies on climate development and to what we just heard from IPCC. I will look at decoupling from an economic perspective, decarbonization up to the complete exit, if I may use this bad word, a fossil fuel exit, of course. What can we credibly say about it? What is a solid foundation for obtaining reliable results in climate economics? I'd like to highlight that the reference pathways, as used by IPCC and others, depend on economic variables which we should treat as endogenous variables, such as income, population, or consumption. To derive those, I suggest looking at our core theory at first principles to see what is a solid foundation for robust conclusions from economics. We should acknowledge that economic and ecological systems are closely interacting. And for this, we need to think hard. Thus, here is the thinker. No similarities with the speaker. You might wonder whether the muscles help thinking. I don't know, maybe yes, maybe no. If you look at the former governor of California, maybe it helps with climate policy. He was initially named a poet, which would probably not really reflect our writing, at least not the writing in English, even when we know a lot about the issues. I think it could also be called the doubter. Of course we have doubts, we have many doubts, but we need to address these doubts, the many concerns. In times of information overflow, we need to get straight messages. And then we need to communicate. We have to communicate with these persons, with these people. These persons have a different background. They live under different constraints. They were selected by a different mechanism. What counts for them are majorities, re-election, visible action. They do possibly not primarily care about the core results of economics, maybe not about the main results that we want to accumulate. Can we reach out with our thoughts and our wording? What do we have to offer? Pareto, Pigou, prices, markets, all great, but first of all for us. We are of course right in insisting that efficiency is key. How could we as economists not advocate that an important goal be achieved at minimal cost? Here we are united all together. But let us acknowledge that some of our wording does not always sound extremely attractive to everybody. The messages from economists are often not well received. Often we encounter hostility from business and environmentalists at the same time. While actually we wanted to reconcile them, we wanted to bring them together, show similarities, show that the trade-offs are not that severe as usually put in the public. Hence, we have to probably adjust our wording and to see how we can improve our communication. Let us then turn to real people. What is more attractive for them? Different issues. Limits to growth, population bomb, degrowth. Alarmism is popular. Some natural scientists are strong in that. They reach out. These messages are heard, but they can also be a problem for us. Some of them make sense, others contradict our results in economics. And yes, the public cares for equity and fairness. In fact, in policy, people care much more about equity than they do for efficiency. The public cares a lot about equity and fairness. Why is this always or mainly or only with the environment? Not all the arguments are honest, but they play a big role in policy. We can and should adapt our policy designs. We have to accommodate the equity and fairness concerns. We should also address the great ask questions, if I may call it like that. Why consider marginal changes when carbon emissions are wrong in the end? It is about the transition, about transforming the economy from a dirty to a clean state. Well, it's cost and benefit during the transition. Here are some facts about CO2 emissions. On the left, you see global CO2 emissions are on a record high. We have seen a steep increase since 1990 on a global scale, which is surprising, but this is the period where we wanted to do climate policy, in fact. On the right, we see per capita and per region values, which differ, as we know. We see some decline on a high level and some rise and decline on a lower level. Per capita emissions have behaved differently from aggregate emissions, so that we need to include population growth in our picture. So this is what I want also to include then in my theoretical approach, but let's first also have a look at the different regional levels which differ from the aggregate level on a world scale. We see CO2 and GDP, our couple. On the world level, we see a relative decoupling, strong economic growth, about 3% at the time, but still increasing emissions, which of course is contradicting our aims. Economic growth at the country levels was mostly positive as well. As a first example for decoupling, I'm happy to present the UK. UK shows decreasing emissions while still having an increasing income. Sweden is better known, the example is better known, it's about the same, absolute decoupling in the region of Sweden. And then we have also the example from British Columbia, which is often mentioned, with a mixed evidence on emissions, but population is also a factor in this case. I might say, well, these are some positive examples, but decoupling needs to be in all regions and needs to be much faster. And this is of course correct. And this is why we have to now see what can be done in the next decades. On this slide, we see some predictions for future development. On the upper left, we see the growth rate of the world economy, which is still positive in the future decades and probably centuries. But actually, to analyze this properly, we have to employ endogenous growth theory to see which of the paths is actually accurate. This will depend on innovation, on investment, and also on climate change. On the upper right, one sees population development, which is predicted for the future. It is foreseen that the population will stabilize at the end of the century, but importantly, during the transition, we will still have increase in population size on a world level, and this has to be considered in our analysis. And in the lower left, we see what emissions we'll have to do in the future when we want to obey to the climate targets. These emissions have to decrease. They have to decrease rapidly, something which has never been seen in recent development. We have to turn around development for emission here. Decoupling is very ambitious, no doubt. But is it too ambitious? Is it impossible? I suspect that many, maybe also many in this room, tend to think that it's too ambitious, that it will not be possible. It will not work, it will not be possible, not so fast. But why? Because we are cautious, because we don't want to hedge our own beliefs, maybe? Strange, why are we not convinced that this could be done? So I think we have to be clear, because climate and energy and environmental economics should actually be clear on this, how we see the development of future climate policy. I'd like to come back at the very end of the talk to exactly answer this question. When people have a first look at decoupling, what they do is kind of decompose resource use in, say, 2 ratios and 1 quantity. And this is what I call decomposition logic. If you do the Kaya formula or the iPad formula, then you have something like a decomposition. And this can be misleading. This can be dangerous because it leads you to wrong conclusions, or may lead you to wrong. It ends in quantity couples. For example, this GDP energy use. Over time, long-run growth and living standards strongly associated with rising energy use. Especially if this was the case, then of course, and if fossil fuels are very important, energy supply, then it becomes difficult. I mean, I live in a city where the 2000 watt society is actually a goal, so we don't necessarily believe that this is true. Even worse or more pronounced is the couple resource use population size, and here a very sharp statement, so we can only support a limited number of people in a sustainable manner. We have a choice, many people which are poor or lower people, we have a higher quality of life. And then another couple, energy couples, that energy substitutes for, which of course are correct, but it's not only energy which substitutes for energy. And here the example of nuclear power, so that we should have this source in order to mitigate our climate emissions. So, well, I would rather, of course, prefer to have Scottish wind or Spanish solar here, but it's just one example I took out of literature. When you see all these couples, no prices, no markets, then you ask, really, is this what we should think? How many pieces should we look at? And how detailed should we decompose the whole thing? And then, so how many pieces should we cut our sausage? And then, at which pieces should we look especially? And of course, we should look at things that we know very well. Prices, negatively sloped demand curves, substitution, sectors changing, capital accumulation, induced innovation, all these things. So, in fact, the whole economics is missing so far. Here we are united, here we can agree, I guess. So the next question is then, which economics? Carbon pricing, yes, we heard that and we want to support it. But then we start with which level? We have a diversity with which, it's not such a problem, but some of the suggested prices are way too low, in my view. Profile, mostly we would agree on increasing profile, but some colleagues have recently claimed otherwise. We should have a high price and decrease. Then should we have country differences? I will argue, and I will come back to this, that probably we should allow for different policies in different countries. What kind of a model are we using to motivate this pricing and motivate our policies? It cannot be that we have a static model which is partial, so simple supply and demand will not work. We have to come with a more rigorous and a more rich approach, and this is what I actually will do in the main part of my talk. Calibration. I will not go much into the numbers here, but I see so many people presenting with outdated numbers and with using wrong predictions, and one actually has to update them very frequently. There is a revolution going on in renewables, and when one has slides with some numbers, one has really carefully to check some months later how these prices have moved, because they move very fast. How should we talk about or think about other environmental policies which are non-pricing? Some of them have been faster and they have been effective. So I guess they work in the right direction. They have induced some technologies. Technology also, I think, is a very important driver in the whole thing. So we shouldn't necessarily think bad about them. The same with the Paris Climate Agreement. Of course, it's not exactly what an economist would write, but I think it's still a great achievement when you look at the international decision making. Equity and fairness, we already had it. We have to include it. And in the end, of course, it is good to have diversity, to have a discussion among colleagues how we should frame these things, and we like to fight a lot. But in the end, it would be better for public communication if we could agree on some basic pillars and some basic messages. So let me talk about my view on the building blocks. So I have put some colors here first. It's now more in the rainbow color. And one point I want to make is to include economic dynamics, endogenous dynamics. We look at the time frame from 1990 to 2050, say. There is no such thing as a constant stock of anything. I mean, these things are evolving. They grow rapidly. And they interact. They interact with the climate change. They interact with climate policy. And this is, for me, is one of the crucial things. So we have to look into investment incentives, knowledge investment, physical capital investment, education investment. We have to look into input substitution, and then the sectoral change which is triggered. Also, on the input side, we have to look into resource depletion, because fossil fuels are non-renewable natural resources. And then when we extract and we emit greenhouse gases, we have damages, and we have to see how the climate damages come into our framework. And then, again, we have to address population, and we have to make it endogenous and see what it does to our economy. Further on, it is not that the climate events come continuously, they come in shocks. There is a risk and uncertainty, you never know when the shock is hitting you, so there's there is a certain arrival probability, which you might know, you might guess, and then there is a certain shock size. It might be that you're hit by a high shock or a small shock, and this of course has to have an impact on your decisions. And the same can happen, and I will make a point at the end of the presentation, with policy. Policies are highly uncertain. They are not certain. And this is also posing some problems, but also solving some problems, I will argue. Then further on, it is not that this whole development will be purely continuous. It might be having elements of disruptive behavior. So it might be the energy transition. You know, this is not something which is purely linear. It can be highly non-linear because you have capacity issues and you have the technology development. These things can lead to momentum effects, so it can be faster at the moment in time. First, maybe it looks a bit, you know, sluggish, but when you trigger and you have technical progress and you have political sector and you have markets going in all the same direction, this would actually be my hope, then it would be accelerating. So we have these transition periods which you have to carefully look at, and just to, as a reminder, of course, we are entering the stage of fourth industrial revolution. If we combine the issues in a good way, this could also help decarbonization and decoupling in this sense. Many further issues, we are used to use non-market effects in environmental economics, and then of course I already talked about this marginalism, and also of course we are not want to be stubborn and just look at income. It is all about having a meaningful, a good life in the long run that we want to well promote here. And policies, efficiency, equity issue, then our inclusive institutions means institutions should not be only inclusive on a country level, but also on a global level. There's a big difference. I cannot be inclusive on a country level while exploiting the public commons. And then stranded assets is one of the issues which I also cannot address fully here. These are elements which are actually slowing down the political process because there's lots of interest in the economy and also in policies, and which make transition more difficult. In this talk, then, I will show some main economic mechanisms driving the substitution processes. I will introduce and then extend the basic class of dynamic models, and I want to explicitly show how these shared socioeconomic pathways, how this can maybe endogenous, because I always think we should have an idea how this is interacting with our climate system, and then in the end I will just discuss some policy effects. And this overall should be an updated view on the decoupling issue. Which inputs should we select? On the one hand, when you look in the long run and talk about stocks which are dynamically moving, then you should have a broad view on capital. Physical human capital, knowledge, health could also be included. Also energy infrastructure, the dams and the windmills, this is also clean. This is clearly capital because it's long-lasting and it's also clean. Then with the natural resources, basically force on fossil fuels because they are the causing of the greenhouse gases and less on the others. And with the other inputs, I will basically focus on labor. But actually, I want to start my consideration with looking at capital natural resource because I can rely on a very rich literature, which is the capital resource models, which we know a lot about. So when we look at capital input, resource input, and the third dimension output they produce, when we look at decoupling, then we have over time to use less and less resources, and as a compensation to stay on a constant output level, we can increase our capital stock. So this yellow arrow shows you, excuse me, where you can stay on a constant stock of output, a constant level of output. But of course, it depends now on how the model or how the reality looks like. It could also be that we have no substitution possibilities, or limited substitution possibilities, and then necessarily output will go down to zero. Or if it's, unfortunately, we have a degrowing output, or then if it's going well and the substitution is easy and then have more capital accumulation, we will have a growing output. When we want to determine this, one of the decisive factors in both aspects, natural resource depletion and capital accumulation, is time. So we have to introduce the time index separately and prominently. And this is what I'm going to do next. So I move my two dimensions to the upper right, and I have an isoquant with capital resource and input in place of an equal output. And you see to the upper left, capital accumulation, the capital stock as a function of time, and to the lower right, resource depletion, this is resource use as a function of time. And this is mirrored with a 45 degrees axis. I want to focus on models where the capital accumulation is coming from a separate sector. That means I want to look into this capital accumulation speed. Let's assume we have a resource depletion which is driven by resource markets, maybe also by policy, and then of course it's decisive how much capital we can accumulate in order to compensate for decreasing resource input. If you have a separate sector determining the decay, what is the additional capital in each period, then it might be that we have the blue arrow, so we can exactly compensate to keep our output constant, or we might accumulate more, which is the red arrow, and then we have a higher function, a capital of, in time, and this will allow us for having a growing economy. So this looks nice, but we have probably to formalize a little bit, and I try to start with a very broad and simple approach, and then want to extend it in several directions. So let me start with a two-sector approach where I have final outputs, capital accumulation sector, resource depletion, and households. Final output, very simple, is a Cobb-Douglas. Output Y is given by a constant A, which is total factor productivity. K is physical capital, R is resource input, alphas are the output elasticities, and the epsilon is the share of capital which is used in final output production. 1 minus epsilon of capital is used in the capital accumulation sector. Here I have constant returns to capital for simplicity. 1 minus epsilon times K, and the productivity B gives me the new investment goods in each period. Resource depletion is a standard hoteling. I have a given S0, I have a stock which I can extract, and whatever is extracted, my R depletes and diminishes the stock correspondingly. And households are assumed to have a constant traditional CIS utility function. Rho is the discount rate, 1 over sigma would be the constant elasticity of intertemporal consumption substitution. When you do this, then you get an equilibrium path for output, the growth rate. The growth rate looks like this, and we have in our diagram, we have a locus where I can show the capital as a function of time, which keeps the output constant. This would be the blue line to the upper left. And we have an area where the output is growing, and we have the blue area where the output would be decreasing, despite of capital being built up. And if we assume that under very general conditions, this would be something like a positive growth rate, then we have to assume, and this is when you pick some numbers very likely, that alpha beta minus rho would be a positive number. And if you do this, if you have positive growth and you have a decreasing resource input like a hoteling path, then you would get, of course, when we go out of this blue area, after the red area where you have positive output growth, together with the hoteling, we get a decoupling of output from resource input, which is all going under market conditions. Okay, this is the first approach, but you will say, but, yeah, many things are not in there and have to be added. One of the first concerns of some people were that, well, maybe this Cobb-Douglas is too optimistic. We have poor input substitution. It's actually harder to substitute natural resources in the final output. So it could be that we have poor input substitution indeed, that I would have to write it in a more general way, my output production function. I can keep my investment function for a while. And then you see on the upper left that, of course, the isochron becomes steeper and means that you have to build more capital in each period in order to have output constant, or even more capital to have a positive growth rate of output. And this faster capital accumulation in one sector model, you will not achieve it because it's not compatible with incentives, but actually in the two-sector economy, it could happen by poor input substitution. What actually happens is you will have a decreasing epsilon. Capital is not only built, but it's gradually the shares of capital in the final output sector and the investment sector, they adjust. And it could be that some capital is reallocated to investment, and then this would trigger additional capital accumulation. But of course, indeed, so this would then support decoupling, but of course one has to embed it in a total model, in a final solution, to see what the equilibrium outcome is, and this is what I will do in the next step. And then another but, what is not yet included, of course, I talked about climate, is not yet included in the climate change, of course. Where is it? How are we doing this? Now, resource use is causing pollution, and this is accumulating a stock pollution problem. And this now, the stock causes trouble to the economy because it's cost. And more traditional models have assumed it decreases productivity, and the growth models now more and more assume it is decreasing the capital stock. And then there has been a debate, is it now one or the other? I would argue it's both. And to illustrate this, see on the left side, see a man with a machine and a house and maybe a road. So this man is productive because the capital is there. On the right-hand side, house is destroyed, no machine, there's no route around. So it's not productive because capital has been lost. And to the upper right, you see some images what happens when you have a hurricane or a drought or some things. You lose part of your capital. And the distinction between the two is whenever capital cannot jump. So if it's gone, you need to save and invest for many periods to get the same amount of capital after you have lost it by a climate event. Let's introduce this in our model. Let's assume that we keep many of these elements constant, but I want to have an addition in this capital accumulation. I want to introduce the stock pollution. So capital accumulation would now look like this. I have the same as before, but I have a climate-induced depreciation. So this D would be a depreciation rate, and it depends on P, and P is the pollution stock. And of course, I have to find, as we had it before, the damage function, this H function, how this relates and how much damage is lost, how much capital is lost with climate change. Resource depletion, as we had before. Now the stock pollution problem looks like this. We have resource extraction every period, leading to an increase of the pollution stock. Pollution stock develops according to extracted quantities. Now I take a damage function, which is not the only one. We have explored several possibilities, but this is one which is compatible with balanced growth, which is convenient. It still is a convex damage function, also this denominator takes some convexity out of the program, but actually it works out quite neatly. And why does it work out here to use this damage function? Well, if you look at the growth rate of the output in this model, you see that we have a relatively clean Keynes-Ramsey rule showing output is determined by the same factors as we had it before, and now we have a climate damage with theta and eta being subtracted from capital productivity. So we have endogenous growth with climate change when provided that this term is still positive, and for many countries and for many periods might be true. For others, probably already this is maybe critical. And if this is now the picture for climate change, of course the problem that we have is because we extract all the resources from the ground, and then we have this pollution problem. We should probably decrease the amount of resources which we extract. So if we limit now this S0 to S0 prime, one way or the other, we could limit the extraction paths in the beginning or in the meantime or continuously, then of course we would have a positive growth effect because we have less pollution affecting capital accumulation. And at the same time, of course, whenever we decrease our resource inputs, we have a negative level effect. So this is actually, when you think in endogenous growth terms, this is often the case in policy evaluation. You have to evaluate a negative level effect and a positive growth effect, and for the log utility you can do this relatively easy. You have to calculate what actually is the result when you do these policies on the final economy, and say you can spread these negative level effects out so that you have each period you would have some bit of a negative level effect, a bit positive growth effect, and the overall effect might be indeed very minimal. Emission taxes, our main instruments. This is fine. Of course, in a static framework it is, but in a hoteling framework we do know that there might be some problem because we have a supply reaction. And it might be that the resource extraction path is just shifted, and actually the total quantity extracted will not change, and this would of course be a problem. In this example here, we would have a preponing, the resource extraction would be preponed, and in the end the whole thing will be extracted. So one has to be careful when applying taxes and when doing this tax policy in a hoteling framework, dynamic framework. One has to probably extend the model or combine the policy with other policies to avoid a simple shifting of the extraction profile, and then this will not help in the end. Backstop, I don't know, backstop is also not a very good word in England at the moment, I think, but here it was a good word. At the time in the 70s, people thought, well, once in a while there will be a technology taking over everything. It would look like this in my picture, but I think it's a fair assessment to say it has not materialized so far, it will not in the future. So it will P, that we have very good substitute for fossil fuels. We will have possibilities to produce in a different way with different energies, but that everything, well, once in a while everything will be taken over. This is quite unlikely. So I think in several sectors we will have very good substitutes, but not perfect substitute. Backstop is a perfect substitute, but we will have situations which come closer to this, and maybe in aviation and some other activities we will not so fast, and it will not be so soon that we will have a good backstop technology for such activities. We can integrate climate shocks. As I said, sometimes these things do not come continuously, so they come down here. I have very big shocks, just to show you. I mean, that would be a major things if you drop in capital, if you go to lower left. So we could do this in a Poisson process, that you have an investment which depends on time, and then we have an increment which is part of a Poisson process, which once in a while hits you, say a Caribbean island where capital stock is destroyed. And then, of course, you will have a different frame for the capital resource substitution. What is important here is to say, well, if this happens and if people are rational, which we assume, they can integrate this uncertainty into their decision making, and they will actually probably build more capital, just to have precautionary saving, have more capital, so when the rainy days come, they have something as a buffer which they can use. And the same is actually true for the Wiener process. We can have a Poisson plus a Wiener, so it can be like this continuous type of stochastic, but with physical capital maybe a bit more difficult to motivate how this should be happening, especially when it's moving upward. Okay, also here with these models one can integrate. Even more exciting, or also exciting, is the disruptive development. This comes from a class of models where we have different equilibria. We have stable equilibria for a low and for a high capital stock. And in between we do have what we call an overlap region, where people just, well, it depends on expectations. When you believe in the clean future, you will take the one trajectory, and you rather believe in the brown past, you think we are stuck with fossil fuels, we'll go back to the low equilibrium. So this is a class of models which is very attractive, but is of course more difficult technically to deal with. We can show how we can generate momentum effects, which actually accelerate development. And surprisingly here, we got also a distinctive role between taxes and subsidies, which usually, in other models it does not come, but the subsidies actually give a different window of opportunities, and this can be interesting, and this is kind of clear when you have this transition phase with lots of non-linearities. Subsidies have a role also on economic grounds here. Of course, one should not give subsidies to things which would have been done anyway, but a directed subsidy could help to trigger such development here. But let me come back to the main model approach, where I want now to add labor. Just to say production, I'll come back to the Cobb-Douglas. And I say now labor L is introduced. I have a part of labor psi which is used for final output production, and I have a part of labor which is used for my investment. Abstracting for climate change for a model, I'll come back to it. Households are the same. Now what happens here? Well, if you look at the capital accumulation, we get a scale effect. Scale effect on growth, so the more labor we have, the higher is the growth rate. This was the early phase of the first generation of growth models, where labor, of course, has a growth effect because you have these scale effects in production. We go now in I want to integrate labor in a more sophisticated way, but it shows that indeed, when we are smart and we allocate labor to productive uses, then labor is actually the ultimate resource. Of course, if we are very stupid and we have lots of unemployment and we have lots of unskilled labor, then it will not work. But if we are actually exploiting the resource, and not only see that people are polluting, that they're also producing solutions, then this can be a major source of development. So this would be here, and then you can say, well, if you include labor into capital accumulation, you should also include resource use in capital accumulation, because this makes it harder. And indeed, when you have resource included in the capital accumulation equation, then you have a drag on capital accumulation, while with the population, so it depends on which one is stronger. I want to include this now in my final model approach, and also I want to extend a bit, because so far I did not have endogenous population, and I did not really focus on innovation. I think innovation is key. We had Paul Romer winning Nobel Prize. I think long-run growth is driven by pushing the technological frontier, so we have to think about innovation. Now this looks like this. This will be the final model slide, so then we are done. But actually, well, it takes some steps, because now I have to change a bit my setup. Final output is produced by labor, now new, capital as I had it, and now I assume that we have intermediate varieties to foster the aspect that we have not only growth in quantities and inputs, but also in the diversity of inputs, like in the Roma model, that we have an increasing variety showing the gains from diversification. So actually the resources are now in this heterogeneous intermediate goods, and this gives another rise of a growth process and another growth engine in the economy. So exactly this intermediate goods, so labor is used in different sectors, as you will see. Labor is also used to produce intermediate varieties together with natural resources, and here we assume again poor input substitution to make it a bit more challenging for the whole thing, and this will trigger then sectoral change. So here the more resources are depleted, actually labor will have to move to other sectors during the growth process. And we take symmetric varieties so that we can have a similar handle. So it depends on the average quantity of an intermediate good and the total number of varieties, which is capital N. Capital accumulation simply modified. Now capital is the same good as output and consumption, so whatever is not consumed and not used for depreciation is actually adding to the capital stock. I do this because we have now a separate thing which is accumulated, which is the varieties. So this is now the growth engine replacing my physical capital engine, and you will see this how it works here. So N dot, this is the output of the research sector, depends on skilled labor age and resources as inputs. And also here I have assumed a Cobb-Douglas production function, which might be some hard assumption, because I don't know how important are the resources for the research lab, but also this could be a cautious assumption, just not to overlook a mechanism which could holding back the main development. So then also have N, so the stock of knowledge is an input, so this is the knowledge spillovers in research. But I take this exponent Q, actually I take it as a function, and it will be lower than unity, just not to have too many spillovers which would generate a too easy growth rate. H is not a stock, so it's just assumed that I convert some of the labor. I cannot use all the labor in the research lab, but some labor I can use in the research lab, and it's just on-the-job training. People have to go to school 1 or 2 days per week. This is this kappa, so that I can have here a labor input. And you see the growth rate, G, of the of the number of varieties is G, and it's given by the 2 inputs, and of course given by the last thing, N to the Q minus 1, which is a drag. It depends on how large the knowledge spillovers really are. Then households are a bit more complicated in this case, because I have also, besides consumption, which is now a log, I have to introduce fertility. I have have a probability of die with a discount rate, and I have a joy of birth flow, B, a little b. Is when you enjoy birth flow, then you have a little b, and how can you produce birth flow? You have to devote some labor to household work. So this is the LB, this is my work in the household, has a productivity epsilon, and this is the output elasticity. This is for child rearing. And my productivity B, this is also an interesting factor, because with the B in this child rearing comes in something which I want to now stress next before I come to the conclusion of this model. It is that these are market decisions, but we do have many externalities also governing development. And these are things which are not going over the market. So this B is especially, so I also want to rely on all the literature. And also have to have externalities, of course, in all the environmental sphere, and I do have externalities in knowledge. And whatever is assumed there also has a big impact on what's in the end coming out. So these are my normal market effects. Pollution stock, I already know. Knowledge diffusion, household productivity, so it will look like this. Pollution stock is as we had it. For knowledge diffusion, I assume a function Q, and actually so knowledge spillovers should be less than proportional, and moreover they should be depending on sectoral change and on the share of dirty production. Because we know this has an impact from literature, this has an impact on knowledge diffusion. I can accommodate this, and my theta here, theta is showing how big the drag is of factors hindering the knowledge diffusion. And the last bit is my productivity in household, in my child rearing. There is a congestion effect, which is actually quite well described and known. This is well documented by the urbanization. When people move to the cities, they have less kids because of this congestion effects than others. And there is also a spillover from average birth flow, social norms, but also kind of institutions in child rearing, which play a role here. So, taking all this together, this was now a lot different elements, but I want to show you now what it gives you. First of all, you can solve for the long-run innovation rate. And what you see here is that the productivity of labor is crucial. I have productivity of labor in the research lab, of course, is my gamma, and then also productivity of labor in my household action. This is the epsilon divided by this congestion effect. And I have the zeta, which is important. This is the knowledge diffusion speed, and also have my omega, which is the elasticity of substitution. So this kind of a nice solution of a quite complicated model. And now when I solve for the long-run consumption per capita growth rate, what I get here, there's two components. On the one hand, it strongly depends on my innovation rate, and then it depends on a second term, which I call, well, this is the drag of resource use, or which I call the element of decoupling. So if I put in rough numbers, the first is almost like entirely the G, so this as the Q is close to 1, so it's almost the whole consumption growth rate is driven by the innovation rate, very decisive. And this is going on independent of what I do with my resources. And the second term is my decoupling. So rho would say how much is my speed of decrease of resource use? How big is my speed of decoupling? Say I increase it from 1% decrease of resource use every year to 5% decrease every year, which is would be a very sharp movement. Then I have to find out what would this do now to my consumption growth rate. And now funnily I come to a very similar number than you mentioned. Because when I take this 1 minus beta and 1 minus alpha minus beta over gamma, this is about 1 over 20. So if I do this increase with 4% percentage points and I divide it by 20, then the effect, say, on my growth rate, which was before 3%, would be then 0.2%. So from 3% I would go down to 2.8% consumption growth rate by this policy, which is a very sharp one, because each year I want to reduce resource input by 5%. Now, to summarize here, population, as you probably did not see all the details, is included, is accommodated. Population is growing actually here, but I get also the demographic transition, I can accommodate that. Growth is driven by innovation, I think this is realistic, and the last term is given the resource use. Now, coming back to my small calibration, to my small example with the numbers. If I calibrate, if I pick numbers which more or less are reliable, I can replicate the growth rate of the world GDP, about 3%. I can also show that when I do a stringent climate policy, the growth rate is a little bit lower, but insignificantly lower. It's a very small amount which we lose. Importantly, what we should compare with is not that we have a business as usual, which is just what we had in the past, but we should compare it, of course, to a state without a policy, and this would also be less growth. So this is actually probably even reducing it more, or even reverting after a while what I have as a growth effect. And then what I did not include now in my general model are these effects which I explained before: backstop technology, momentum effects, risk and uncertainty, which lead to additional capital input. So all these things are not there. But asking now, as we have it, and you already mentioned it, that we have it on a global level, growth losses are so minimal. And if you compare it to a state without the action, it's even less. What is it then, makes this so difficult, the whole thing? And of course, it is that the world is so heterogeneous. The world is not one economy. There are different economies and different policies. So I have, in the last part of my talk, I have to address this. The huge variety of different countries, different states, and of course each country being anxious that it has to do too much against the others. This is a huge issue, of course. First of all, when we look at the world as a north-south model, and say there's countries of the north, of the south, it is clear that we have a huge gap in incomes, and that we have in some countries in the south a huge impact of climate change, while in others it's less, and in some countries of the north it's also less. So this is the heterogeneity, so there's some aspects of this heterogeneity. On the other hand, a more positive side, we do have knowledge diffusion between the different regions. And we have empirical research showing that when we have knowledge advances in one of the regions, it translates to other regions, because a relatively inexpensive way to decrease your abatement cost is to import knowledge, and then this would lower your cost of the climate policy considerably. This is actually also one that we have to. So, for example, for China, we came up for numbers up to 80%, that due to international knowledge diffusion, abatement costs are lowered in China. Okay, so this is the thing here. Now, next we have to think about our carbon pricing instrument again, about this uniform and non-uniform carbon price and how we should do this. So our general wisdom is the following. If I stick with my diagram which I had before. So resource use, capital, optimal cost minimal, optimal to achieve a given output. If I change relative prices, I go from the flatter line to the steeper, the dotted line. And then, depending on how the adjustment is of the different countries, about the adaptive capacities, one country will abate more than the other, or one firm or one individual, depending on how good the substitution is between resources and capital. This is common wisdom. Now, it might be that this is not really the issue. Electric cars have more or less the same price everywhere, solar panels have the same price. So maybe this is not most important. More important is the different levels in income. So some countries are richer than others, and maybe they have kind of the same isoquant. So when we do now our carbon pricing and we have a shift in relative prices, might be that we probably get something like an equal abatement in the optimum. But this is now what people worries. People are worried that the poor country should do exactly the same abatement as the rich country, and this can now be translated in a situation where you have to invest in this way that you have to consume less. And when we now use the concavity argument of our basic utility function, then we would get, of course, that the sacrifice of the rich country is lower than the sacrifice of the poor country, the less developed country. So an equal abatement decision and an investment that you have to do, it makes, of course, an asymmetric input on your well-being. Now, translating this in a more general framework, we can say, well, here, this is what I have on the right side, abatement cost, maybe the same for the two levels, but the impact on utility is a different one. And now, if you want to, on the lower level, I have these different utility losses. This is the orange arrows. If I want now to move them a bit closer together, this should be indicated by these green arrows. What happens then? Well, I can do it either by transfers or allowing these two countries or two units to have different pricing. Transfers would be good. I can have a uniform carbon price and then allow for transfers, but at the international level, it's very hard. And it would be big amounts. If you calculate what kind of transfers it would involve, nearly impossible. And when I talk to people, they would never think that richer, of course, there is some money flowing from rich countries to less rich countries, but a carbon pricing would generate huge revenue. And that the substantial part is then distributed along these lines cannot be. So then, if this is not possible, then we should allow to have different countries, different pricing, different policies to have, say, an equal sacrifice for the climate policy on a global level. And we can also extend this argument further. We can, this is kind of a ability to pay argument, which is often used as an equity principle. There are more equity principles around, and I believe the debate and this discussion about equity principle has been abandoned too early, because it can help to find out how we should deal with the heterogeneous countries. And one of the conclusions, so we have a climate calculator, you can use it, play around with it if you like. So this would be a comparison in 2030 between different countries, what they have promised to do and what they are supposed to do according to our idea that we should have an equal burden sharing. And you see the red is the deficit, and some countries are a bit more red than others are, and we have some blue, but this blue is only applying if they really do the policies that they have announced. So if you have, you know, if the NDC is some kind of contingent, then you have some remarks. So this is just a projection if you compare what countries have announced with what actually they should do, and then you see a bit how this heterogeneity can come through. Now, of course, a country can do more by either, you can have the same strict policy and have international transfer, or then you should abate more domestically in order to fulfill this equity criterion. What about CO2 tax? I'm coming now closer to the end. I think I should then also, you have the idea, you know, we have two countries here, Sweden and Switzerland, two different countries. You see the tax rates have jumped. You see it in the case of Sweden for household industry. You see it also in the case of Switzerland. This is this grey thing. In the case of Switzerland, it's kind of a mechanism which is implemented, but it's not as clear. As I say, every time the carbon tax is increased, the government has to approve. And you never know who's in the government and whether they approve or not, so there's huge uncertainty. So what I conclude from this period of the taxes already being placed, that tax rates jump. And it comes at irregular dates, and you don't know how much they jump in each case. So this is kind of a problem for private investors. So I take from this, when we think about these individual policies, we are used to have our neat models, and I do all these models, this is for everybody. And we deliver an optimal policy design, and then we go to the policymakers, to the government, and say, now this is to implement immediately, and this is what it should be forever. And actually this is exactly not what happens. It is completely different. So for example, what I do have here, we have some problems identified, but like the climate problem identified. And then we first propose some policies probably, or some views on the issues. Then the public becomes a bit of alert, because the politicians, they don't react immediately. The public becomes alert. Maybe in political debates you have some first discussions. Then, very importantly, technology will have some incentives. If they think this is now really becoming serious, they will develop something to solve the problem. And then, of course, when new things come up, the old things will try to hold against it. Then we have all this lobbies and the campaigns, the stranded asset problem. Then this whole bazaar begins, back and forth. And then, of course, it also, because I said politicians react very closely to public opinion, it depends who wins, who is more convincing, who has the media attention, who can convince people. And then also technology may react. Maybe if technology now really thinks we have to move on with these new technologies, then they will go faster. And if the engineer think, you know, we'll go back to brown, then they go there. So it depends a bit. This is a very uncertain outcome. So policy, what I want to say here, is not really what we had in mind. We put a carbon tax and then we stay there. It's more, it can change often, frequently. And when we look at this, it's actually funny. I mean, this is just a picture about this sofa with two cushions. We've always done it this way, and we know that. So we used to do it, actually, we do pigou taxes all the time, and we like it. But actually, the other one, stochastic taxes, this is what's happening. If you look at reality, tax rates change, especially environmental tax rates change. And we have to describe and to probably also to motivate how this is happening, how this is affecting the real economy. And it is not necessarily a bad thing, if I may add that. We know we have the feeling a reliable policy is the best. Then the private sector can adjust its investment consistently. Here, when you have this stochasticity, this uncertainty, you also threaten people a bit. It's not nice, but it's not very a nice policy. But the huge uncertainty you have about certain technologies creates incentives not to invest in that direction. So this stochastic thing could also, I believe, once we are now moving with green technologies, in the end, when the brown technologies become relatively unimportant, we could remove them relatively quickly by just stringent policies, because then they no longer have a political lobby which is so strong and which would influence voter that strongly. Let me conclude. I have some lessons on decoupling. I wanted to show with my model that resource scarcity, pollution, and environmental policies are compatible with economic growth, but with economic growth which is based on science, on knowledge and on labor, not on material. I have the conclusion that the dynamic effects, which I really wanted to push during this lecture, tend to be ignored, misinterpreted, or underrated. And I did not, in the main modeling, I did not refer to what I think is also important. I did talk about poor import substitution. I did a bit talk about risk, but I did not really include it in the modeling. These momentum effects are important, and also, of course, this diffusion and the green expectation. This is important things which drive the transition towards a carbon-free future. Lessons about decoupling for policy. 4 of them. I think stringent carbon policies affect growth only moderately. We have it confirmed by our, say, simple model, but maybe a model which includes many elements. We should design policies in an efficient yet equitable way. Maybe there is a small trade-off, but not everywhere, and we can try address it. We should be a bit more tolerant with policies which are not exactly what we like most. Policies in the end need to be workable, they need to shoot in the right direction, maybe they're a bit imprecise, but still they are helpful for decarbonization. And as I said, the stochastic thing is not really nice, but it's realistic, and it might even help and accelerate our decoupling. Well, coming to an end, as I said, significant decoupling is needed. Is it ambitious? Is it too ambitious? I think it is ambitious, of course, but it can be done. It would be great if all the EAERE economists could be united. We could all agree that stringent climate policy is feasible. For me personally, it is clear we are simply going to do it. And with this, I would like to thank my team, my co-authors, my colleagues, EAERE, and you for listening to this talk. Thank you very much.